Okay, good evening, everybody. I've spent a lot of time thinking about how to present this particular video because most of the floor equations that I've seen have been just done purely analytically without regard for the graph. And so what I'm making the assumption one could do is sketch the graph of both of these functions, x squared plus 1 and 2x, and use that sketch to glean the relevant information from the graph. Now, if you couldn't do that, then that's not a fair way to do things. But it is, if you can sketch a decent graph and get the information from the graph, that's a valid approach. Now, having said that, I'll let a computer draw this, but this would be a pretty easy graph to sketch by hand. But just to be professional, I went ahead and let the computer do the graphing. I know that sounds disingenuous, but this is a fairly easy graph to sketch by hand. That wouldn't be scaled as well, but you can see that it's going to intersect exactly at 1. If you said x squared plus 1 equals to 2x, the only solution is x equals 1. And you would also know if you sketch it by hand that the blue line, which is the 2x line, is always going to be to the right or sort of underneath the red graph, which is the x squared plus 1 graph. So again, you could come up with a decent sketch if you wanted to take the time. You could put it on graph paper and do a pretty knockdown job. Turns out you don't need a perfectly scaled graph or a perfectly scaled sketch to perform this task. Now, so again, a trivial problem if you don't have this floor function notation. X squared plus 1 equals 2x has a single solution, namely x equals 1, done, right? Unfortunately, we have these square braces or these half square braces, which denote the floor function. Now, another way of talking about the floor function is just thinking of it as a mapping from any real number to the integers. Now, Z here stands for Zahlen in German, I think, and it means the integers. Now, most of these type of problems just map to the natural numbers, but this literally means no matter what real number you hand it, you will produce an integer. And 0 is included, of course, as an integer. Now, for example, 3.2, the floor of 3.2 would be 3. The floor of 3.2 would be 3. I've heard this called the truncate function. You're chopping off the decimal 0.2. Now, also proper fractions get mapped to 0. For example, 3/4, its integer part is 0. All right. So the floor of any proper fraction, any positive proper fraction is 0. Now, again, having the graph really helps you quite a bit. In fact, if you take a look at this graph, and again, make the assumption you could have sketched something very close to this by hand. Otherwise, the approach, just to let the computer doing it with no idea how to do the graph would be an invalid approach. So you can tell almost immediately that the solution set for this has to be contained in the interval 1/2, 2. Now, why is that? Right here at 1/2, and that's easy to determine. 2 times 1/2 is 1, right? Anytime you're below x equals 1/2 on this graph, you're less than 1, and that means you have a floor of 0, right? Now, the red graph right above it certainly has a floor of 1 in that region from 0 to 1/2. So for that reason, the floor of 2x is equal to 0 in the interval 0 to 1/2, and the floor of x squared plus 1 is equal to 1 in the interval 0 to 1/2. So it's not part of the solution. Now notice here it is crucial to exclude 1/2, because if 2 times 1/2 would give you a floor of 1. All right, and then so again, we're excluding the closed interval 0, open interval 1/2. Now also, just before we move on to the next screen, notice that at 2, the floor of the 2x function is equal to 4. 2 times 2 is 4 in the floor of an integer is the integer itself. But notice the graph indicates you're at 5 up here. So the floor at 2 for x squared plus 1 would be 5. So that implies that the interval, we already know that the solution set will be contained in the interval 1/2 to 2. That's something that we know right now, that the solution intervals will be contained in the single interval 1/2 to 2. All right. Now let's move along. Okay. Now right here, this one's fairly straightforward also. We already know what happens from 0 to 1/2. Now we have bracket 1/2 to 1. And it's clear that both of these functions have a floor of 1 in that interval from 1/2 to 1. Now, y'all, again, I'm along the x-axis here. At 1/2, this graph is equal to 1. The linear graph is equal to 1. And both of them remain underneath the function 2 all the way to 1. All righty. And again, it's important to, did I do that? Yeah. It's important to have 1 excluded, again, for the very same reasons as last time. Okay. So we now know that closed 1/2, open 1 is part of the solution set. Okay. So far it's been fairly straightforward. All right. Now let's keep going here. Now, perhaps it gets a little more dicey here. Let's see, where are we? Yeah, let's go here. All right. Now, did I manage to not get this all on the screen? Doesn't, yeah, it looks like I had a little bit of trouble here. But okay, y'all, we already know we're past 1, so let's slide on up here and see if I did. I think I killed our space here just a little bit. No, we're doing okay. All right, now you can see right here, it's all about what happens when you cross horizontal lines, because that's what the floor function is interested in, right? So we can see that between 1 and 2, the two graphs cross the horizontal line y equals 3. Now, we don't know what those values are, but we know there's going to be floor changes at both of those values. Now, it's clear that that happens at 3/2 for 2x. Set 2x equal to 3, you get x equals 3/2. Now, in a similar fashion, if you set x squared plus 1 equal to 3, you get the floor change happening at √2. All right. Now, so what that means is that we have to add closed 1, open √2 to the set that we already found. The reason is again, it's pretty straightforward. If you take a look here, they shared the same floor all the way up until the time the red graph got to the √2 point, right? You see, they still had the same floor of 2, but the minute the red graph gets to the line y equals 3, its floor changes to 3, right? And so that's why you have to stop at √2, because the blue graph still has a floor of 2. All right, and that's where I'm doing a lot of talking here, but the graph just says it, right? And so now, in a similar fashion, there's going to be a floor change at 4 for the red graph, all right? And that's going to happen at √3, all right? And so that's why we have to add 3/2 in √3 onto the solution we just created, right? Because for the very same reasons. Again, √2 is where the red graph changed its floor. It went from a floor of 2 to a floor of 3, all right? And so that's why √2 had to be closed parens. But once you get to 3/2, they now have the same floor of 3, all right? And that continues all the way up to these points right here, namely √3, as far as the x-axis goes. So now you see, we're done. I mean, we're finished with the problem just based on the graphical information. Now, perhaps I talked too much. I hope you guys enjoyed that, and I think that an argument for using graphs is based on what's commonly done in algebra books these days. Most people that deal with functions just think of a function as f of x is equal to some expression, one or more occurrences of x, and that's it. That's f of x. But there's actually more or less 4 widely accepted ways to do functions in the college algebra book. One is to verbally express the function, like for example, x squared could be expressed, square the input, add 1. That's a verbal expression. You could express it as a collection of ordered pairs, for example, 0, 1, 2, 5, -2, 5. they would all be points on the graph, and you could list the ordered pairs. Now, that's not a very convenient way to do things. And also, you could just express the graph just like you normally do as a function. So, but the graph is yet another way to express a function. And so I utilize a graph. Both of them represented functions, and we're able to reach the same kind of conclusions you would reach if you did things analytically. Hope you like the approach. Thanks.